I am recording. I hope you can see my screen.
Okay.
Fine.
Well, thank you. We'll take it away for Khan, and I'm really excited for your tutorial.
Okay. Hello everyone. I am Furkan. Actually, we have met. So today I will explain how to use how to couple the intracellular modeling with PhysiCell. Actually, this will be more focusing on the kinetic modeling. So what we have learned so far. So far, actually, we have learned the PhysiCell folder structure, the model domain with different DTs like diffusion DT, mechanic DT, phenotypic DT, and also using the user interface to create the XML file, which is the configuration file. And also we have learned the PhysiCell C++ function. So this will be kind of like this demo will cover nearly all of them. What we will learn the basics of kinetic modeling, which is the OD models, and how to integrate these kinetics models to agent-based modeling, how to control the phenotypic parameters based on the intracellular model, and I will show the related functions which is used in LibRoadrunner, and how to save the intracellular data and how to make faster your simulation, kind of like losing the convergence. So as an agenda, I will talk about 1.9 PhysiCell, and I will explain the integration and add-on, and if we can reach in this one, maybe we can create the basic domain for the demo. So actually, like nearly kind of like and 25 days ago, actually, the PhysiCell 1.9 is released, and in this release, the major features are the intracellular modeling approaches. So actually, it is included the three types of approaches, which are the Boolean network, kinetic modeling, and flux balance analysis as an kind of like alpha version. And in this 1.9, actually, each like the all intracellular, there is a new intracellular object in phenotype, like normal motility or volume. You can just go and phenotype that intracellular or so to reach it. And in this object, there are some mutual function which is using all used which is used by all these three packages, PhysiBoss, LibRoadrunner, and PhysidFBA. Like the start, uptake, get parameter, set parameters are just mutual, and they can be used in any of these packages. Also, there are some specific functions and specific to the packages, like the validate SBML species. This is for OD, and get Boolean variable value function is for the PhysiBoss. So in this 1.9, also each type of package has their own sample projects. In the PhysiBoss has PhysiBoss cell lines, and LibRoadrunner has OD energy sample project, and PhysidFBA is the cancer metabolism. So actually the installation was kind of like hard for us because of each type of each add-on requires a solver. PhysiBoss requires Mabos, which is actually kind of like easy because they provide it. PhysidFBA is using an optimization solver, which is called CoinCLP, and LibRoadrunner, using LibRoadrunner, of course, it's an ODE, ordinary differential equation solver for the chemical reactions. And to install related solver, you need to actually populate the sample project first. For instance, like if you would like to install the LibRoadrunner, you need to make ODE energy sample and then make. So I will just touch briefly other two packages. The PhysiBoss is again the Boolean network, and they it is developed by the a very talented team in Institute Curie and Barcelona supercomputing facility, and you can have the you can find this PhysiBoss part in here, but actually this is fully integrated as an add-on in the PhysiCell. And we had actually an optional morning today session, which Arno did a very good explanation, and actually the recordings are getting processed, and so. Robert has a question: what types of problems can CoinCLP? I think it's only for so I'm not sure. Linear programming is there because the DFBA is there, but I'm not sure the other um, programmings. The PhysidFBA, which is actually a kind of coupling the agent-based modeling and FBA, which is developed by Miguel, and this this package also is added. And also I will kind of like touch an approach how they integrate it, and this also is added as an alpha version to the PhysiCell 1.9. Okay, the LibRoadrunner. So the main the main target, or the main achieve the goal is integrating intracellular kinetics models to the each agent. So cells will have their a kinetic model, which is in ODEs, and they can simulate their these SBMLs. I will explain these SBMLs in later, and then they can change their reactions according to the intracellular entities. To give an example, intracellular oxygen deficiency, which is leading to the death, or also there could be amino acid levels which are kind of like can be coupled with the growth or cell cycle rate. And also this opens a new opportunities to the PhysiCell to use SBML to control or to change the phenotype parameters in ordinary differential equations. So therefore, in future, maybe PhysiCell can be pre-compiled and like distributed like this. So therefore, people can just write their ordinary differential equations, and then PhysiCell can parse it and as an SBML, and then make it ordinary different and solve it ordinary differential equations, and then go. That would be very, very good for the PhysiCell, so that therefore you don't need to recompile again or so. And LibRoadrunner is the solver, and this solver is developed by the Herbert Serra and the Samaji and their team, and we are using C++ API. Actually, this is a package in the Python too. So before we start, I would like to explain the SBML. SBML is the Systems Biology Markup Language. So it stores the reaction stoichiometry information. It can has both approaches, like kinetic approaches, which are the ordinary differential equations with the reaction kinetics, or also it could be storing the pseudo steady state models, which are the flux balance analysis, and those are for the optimizations. As you can see, it's hard to read for the human, and it's parsed according to some rules. So in SBML, actually there are four important parts. There are more, but these four are very, very crucial. The first one is the compartment. So SBML is kind of like looking for the compartment as a volumetric entities. So the chemicals can be present in those entities, and the species are called it's actually those are chemicals, or they can be other kind of like species, like the that they can be, for instance, like ethylene or so. Or the reactions are here, as you can see, the stoichiometric relations like stored like this. Also, it could has the lower boundaries and upper boundaries for the FBA, and the global quantities for the parameters and constants. So the kinetic modeling is, so let's say we have a set of chemical reactions in this stoichiometry. So what we are here, so we are having a kinetic relationship between the substrates and the products, and those can be written as an ordinary differential equation. So in this one, actually, this aerobic reaction is consuming glucose in this rate, and this is the intracellular volume. So, and it is multiplied by the chemical kinetic constants and the concentration of the substrate. And because those are negatives, these are just consuming the substrate. And when we look for the energy, those are creating, and there's an energy use in some in some rates. So therefore, we are having those kind of temporal-spatial simulation. So okay. So the one thing important in this context, actually, in this PhysiCell context, SBML, general SBMLs, like these SBMLs mostly, like the one of the best way to distribute those ordinary differential equation models, when you go to the biomodels and download one of the curated ones, what you will see mostly, you will see is like an extracellular. They have more than one compartment: extracellular, intracellular, mitochondria, maybe nucleus, maybe. So this information is important in future. So, and also the same chemical can be expressed in different way, like in the extracellular compartment, the glucose shows the extracellular glucose, even though those are glucose, they are in different compartments, so they are different species. And also there are transfer reactions between those compartments, like in here, glucose is actually, this one makes it reversible. So I know I consciously wrote this way. So it could go in both way in the transfer reaction. So therefore we need a transfer reaction for those compartments. But in PhysiCell, we use BioFEM for the transfer, for the secretion and uptake, uptakes with uptakes, and, or net export rates, like we did on Monday. So therefore, there is a kind of like a a contradiction in here. So therefore, what we decided is, so the SBMLs that will be used in the PhysiCell should have only intracellular compartments. They can have more than one compartment, like mitochondria or nucleus, but they shouldn't have extracellular, because we are making transfer reactions with BioFEM. So therefore, not all SBMLs are supported, and users need to be very careful about it. And again, not external compartments and not transfer reaction in SBML. And also the mapping is needed between SBML and PhysiCell that I will show. And so as a default right now, those works on each diffusion DT. And so right now, like, because we are making the transfer reactions or the uptake or excretion in 0.01 minutes. So as a default, the SBML solver using 0.01 intracellular DT. So do we have any questions about this one? And then I will go for the integration design. Hi, Paul. Paul, I think, do you have any question? Because I think your hand is...
Sorry, my hand is raised because there's a question in the chat window, and I want to kind of moderate that while I'm still here. Robert Moore asks, what kinds of problems can coin CLP optimize, such as LP, MILP, QP, or NLP?
Oh, thank you. So I think I try to explain. So as far as I know, LP is there, but I don't know the other ones. I'm not sure. Okay. If there is no questions about in this one, so I will go to the integration design. So as an integration design, let's look for the purple and blue part. So we have the microenvironment and we have the uptake and secrete. They are internalizing metabolites as an amount, and this is the biofm part. And when we go for the PhysiCell part, the cells has their phenotypic parameters, and also they can have the kinetic parameters. So I will explain it. And the internal metabolites concentration can be calculated by the internal metabolites amount by divided by volume, uh, because we know the cell volume and we know the internal amount, so we can have the concentration. So what we are doing in here, after we are calculating the metabolic concentration, we are updating the SBML. So LibRoadrunner is an object again, and it can be simulated through LibRoadrunner, but each cell has their own model. So therefore, according to the some rules, let's say there is no oxygen in here, maybe that cell has less uptake rate or secretion rate. Uh, Secretion is not actually affecting, but the thing is, we have a different internal metabolites concentration in each different cell. So therefore, we need to update their SBML. So we have some functions for it. So we are updating the SBML. SBML is again ordinary differential equation with initial conditions. We are just changing the initial conditions to the specific concentration, and then simulating the kinetic part in with a 0.01 time step, and then updating back to the internal metabolites concentration, and then changing the amount, and then therefore that chemicals are used or maybe or created, then it can be secreted. um yeah, I have a question actually. So there will be single biofm file, but a separate SBML file for every cell. No, what I mean is, um, it's a pointer. Like each cell has their own SBML model. And biofm, what I want to, so this is kind of like an overall integration design. And biofm file is the microenvironment file, yes. And each cell has their different internal metabolites. I hope I could explain. Okay, so we updated this SBML in the cell, and then we simulated, and then the internal metabolites concentration changed according to the ODs, and then we go back and change the internal metabolites concentration in the cellular data, getting from the data this SBML, and then changing the internal metabolites. Therefore, we are just um, consuming or maybe creating. And also, one thing is in here important. We can actually control the phenotypic parameters according to the SBML results. I will explain this one later, but this is very cool actually. So we did a performance test. So in here, actually, you can see 50,000 agents are just seeded as a very big blob. And there are 4 substrates. Internalization is on, and 5 SBML species with 4 reactions. And the domain is, that kind of domain is kind of like big, but it's 2D, it's not that big. I just use my PC, and what I want to see, I want to show is, um, in each minute, the output is generated without an SBML. It took like 11 seconds. With an SBML solver, it took like 20. But when I actually got my output in each 60 minutes, what I want to say is 60-minute simulation is here. 60-minute simulated time is occurring is here. It took like 2 minutes. But if I have an SBML solver, it's more than 60 minutes. So again, like this is slow. Yes, we know. So the thing is, then in this point, actually, we need to talk about the intracellular DT. As a default value, it's 0.01 minutes. So what we are doing is we are just simulating the kinetic model in every diffusion DT. So we can change this one. So therefore, I want to explain how it looks like. So I'm just thinking about kind of like Excel is a kind of like pool with a source and sink. And let's say there is a chemical reaction occurring in the cell that is just consuming the chemical. So let's say we have a chemical in here, and it's consumed, and then so let's say this is the first diffusion DT, and because it's uptaken from the environment, let's say it's coming from here, and it's go up, and then the other part, the intracellular DT is coming because it's the same one, and it's consuming. And let's say it's kind of like bouncing like this. So therefore, we are just kind of like having the same DT, and there, because there the convergence difference is not that hard. It's not that different, but it's slow. So because we are always saving the data and overwriting, and then again saving the data and changing and updating, but it's slow. So okay. So when we change the intracellular data, which we will do in the demo, what we will see is a different part. So let's assume that we change the intracellular to the 1 minute, which is like 100 times slower. So how it look like this actually? So again, we are uptaking some chemicals, but we should consume, but we are not. So therefore, it's just like uptaking and uptaking, and then we are simulating one big DT, 1 minute, and then it's going like this. So in the overall, we can just look for the convergence, but so when we look the time point in here, it's very unscientific. But when we look for the overall, it's kind of like making a similar behavior, and this one depends on the depends on the set of reactions. So therefore, I cannot say that like you shouldn't go in like below 6 minutes, or I cannot say like you shouldn't go 1 minute. It depends on the set of ordinary differential equations and set of reactions. So this is so much faster. You will see in the demo, but again, just be careful and just know what to do. So how it looks like. So this is our configuration file, very old and very friendly. And in here, there's a cell definitions in the name of default, and cycle, that volume, motility, and there's a secretion, and then the intracellular part. The intracellular part starts with the name of the add-on. In this case, it's Roadrunner. If it is the PhysidFBA, it's PhysidFBA, I believe. And if it is the PhysiBoss, it's PhysiBoss. And then we are giving the SBML name. So therefore, each cell has a specific SBML. In this default cell has this long SBML. SBML is stored in XML, by the way. And then we are mapping that I will explain later. So this is how it looks. So I just want to show some results. So I have a kind of like a toy model with the 4 species: oxygen, glucose, lactate, energy, and oxygen and glucose consumed, and lactate and energy is created by the reactions. So if so this is very simple toy model, and both are simulated in PhysiCell and Copasi. Copasi is I will show in the maybe second session, is an SBML editor, and also you can simulate the SBML in there. In this model 0, there is no transfer reaction. There is no uptake rate, just solving the SBML. And then this, as you can see, the simulations are giving the same results, basically. In the second model, or the model 1, there is an uptake glucose on oxygen and produce energy internally. Again, it gives the same results with like the Copasi and PhysiCell. So one cool thing starts in here actually. So what I did in the SBML, you can set some events. It's again a feature in SBML. I will show in Copasi. So you can set some rules actually. So for instance, I set a rule in here: if the energy level is smaller than 50, then the cycle rate equals to 0. But if the energy is greater than 50, then the cycle rate it's this. So you can mathematically like assign in the SBML, or you can also use the events. And so this is the result for the cycle rate. After some point, the energy is increasing because of the glucose and oxygen, and then the cycle rate is changed. In the model 2, so there is a phenotypic change. So actually in this one, I didn't implement the cycle rate, the update part, but in here actually there is. So in here there is an organoid, which is like 2D, by the way, it's not a 3D. The lactate secretion rate increases based on the lactate concentration. If the oxygen level is less than threshold, then cells increase their migration, trying to escape from the hypoxic areas. And then if the energy level is less than another threshold, they go to the apoptosis, then they die. So this is the microenvironment part. So as you can see, the oxygen is consumed and glucose is consumed. In here, in the beginning, there is no lactate creation rate, and lactate secretion rate is just 0. But in the SBML, they are creating their lactate, and then they are changing their lactate secretion rate, and therefore, after some point, you can see those kinds of behavior, because the lactate is internally created and then secreted to the microenvironment. So this is how it looks like. We see it as a blob of cell. So after they are consuming the internal oxygen and glucose, as you can see, they are starting to escape from the hypoxic part, and then after they pass the death threshold, they die. Also, in the sample project, you will see a MATLAB file that can visualize the temporal data of the certain area. In here, actually, I just look for the 20 to negative 20x to negative 20 to 20, just a square in the middle. And this is an average intracellular oxygen, and as you can see, oxygen is decreasing through the through the simulation. And in the beginning, actually, they started with 450 and they increased their energy in here. But we don't have any kind of like rule in this model. In the demo, actually, we will have a different, we will have a cycle part in here. But after they pass the death, the motility threshold, they move and then die. Okay, again, this is how it looks. So why I put this one, because I want to explain the mapping part. So in the mapping, there are actually three types of mapping. The first one is the substrate, the one important because this is how we find this is how we map the PhysiCell substrate to the SBML species. And the second important one, the phenotype. So what I am doing in here, we have some tokens specific to the PhysiCell, and then just getting the data from the SBML in the name of this. So therefore, so let's say this one is the phenotypic part, and the DA is for a token for the apoptosis, and the SBML species death rate, and this is in SBML. So if the SBML species is changing, then the death rate is changing. And I have a question, I believe, or no. Randy said intracellular type choices in XML are, yeah, yes, yes, we talk, yeah, Roadrunner, Mobos, or Boolean, or maybe, or no, or DFBA. Okay, thank you very much, Randy. So the SBML phenotypic parameters. So these are the tokens that we are using to update the phenotypic parameters. So if the first letter is C, then it means cycle. I will explain cycle in later. And D is death rate. If DA, it's the apoptosis rate. DN is necrosis, and persistence time, MPT or so. And volume, also you can change the cytoplasm, solid cytoplasm, solid nuclear or fluid fraction in here. So what we are doing is just actually like updating the phenotypic parameters based on the SBML value within the given name. So some of the tokens need some more information. For instance, phase transition rate is the needs to have start index and like end index. So in this given example, the phase transition between the first and second phases is just that given SBML species. For the uptake rate or secretion rate, you can just use the same name in given in the PhysiCell. Okay, I think we don't have any questions. Then I can just continue with the functions. So this is again same format for the all intracellular add-ons. And some of them are just mutual. And the start is just starting the intracellular for the cell. It should be used after the seeding the cell, which will be in setup tissue. And also it is called after the proliferation. You don't need to do anything. After the cell divides, the PhysiCell automatically actually start the new child's the new child's intracellular, the SBML or intracellular. It's valid for all three. And initialize SBML is specific to the libRoadrunner. It is actually reading the SBML. Actually, you will not use. And get values are and set values are two important functions. Get value is getting the value from the SBML, and set value is the setting the SBML. So this part is setting SBML, the tree, and while we are updating the cellular data, we are getting the data. The updates part is just simulating SBML, and I will show how to use them. And get state is just getting the name of the SBML. The update phenotypic parameters is just updating phenotypes parameters according to the given tokens. And validate tokens and species are just validating the given token in case of some typos or so. And validate species just looking for the SBML names and again validates the name. So let's look in here. In this example, actually, as you can see, the motility speed is 0 in here. But what I do is I use MMS token, and SBMS species is in the name of migration speed. In here, actually, when the oxygen is again, I think it scales with oxygen. In the beginning, there is no oxygen in intracellular. After it's taking more oxygen, and then it's actually starting increasing its speed, and so. And this is very similar example. As you can see, secretion rate for the chemical is 0, but we set the secretion rate lactate as so there's a typo. This is the old syntax. So right now we have SSR lactate. There's a typo. I'm sorry. I need to write this one. Okay, what if we wrote if user used the wrong token? Again, it looks for the name that is specified, and there is no MTR in the phenotypic token, so it looks for the motility because it starts with M, and then it shouts an error, or and then stop the simulation because there is no token. There is a wrong token in here, and also the wrong token is given in wrong, and it looks like this. And this is true for the SBML species too. If there is no SBML species in the name of test will not be parsed because this one is firstly looked. So if there is no death rate species in the SBML, then it will just stop and go. So let's go and look for the code together. So this is actually like I have a PhysiCell, the very plain, there is nothing in there. So I'm just opening the PhysiCell, and I just want to make it list projects to see what we have. I will use OD energy sample. So in here, I populated. I have the new main file, new configuration, new core, not new core, new custom modules, or so. And then after I make, it will start. Actually, I kill it. It will start to look for installation of libRoadrunner. If you didn't have libRoadrunner in your computer, then it will actually download the libRoadrunner and put it on the related solver. In this case, it's libRoadrunner is in add-on. Yeah, so this was the thing I want to explain and show. So the related codes are stored in here, librr. So maybe I can just close these ones. So this is the functions that I explained. So we will take a look later today this one. So I just want to look how the code looks like. So so this is the main file, and we have the all things, and the different part is in here, the intracellular DT, the last time intracellular time, and intracellular DT tolerance, and next intracellular update. So these should be in the main file to to be able to run in a specific given time. So if we would like to change the intracellular DT, this is where we need to change. So I believe in future this will be more easy, in very clean, but right now it's manually written. So and also this is how how we can see easily. So and the update intracellular function is the function that is in the custom module I will show, that is actually um, simulating the SBML. So this is the main file, and the only two things differing is this part and this part. So when we go to the custom modules, so it starts with, again, normally. So what you will see a different thing. They have two different includes, which is a need for the libRoadrunner. So if you are using libRoadrunner, you should have these ones. And those are same. Create cell types, set up microenvironments. Those are same. Set up tissue. The setup tissue is the one that we need to be careful, because this is where we seed the cell. No, sorry. This is where we get the cell definition. And this is so after this is okay. We are creating a cell in this cell definition, and this is where we seed the cell, yes, and then we are assigning the position. So the one important part is in here. We are starting the SBML. We should start the SBML or intracellular in the code, because we are saying that this has an intracellular part, and this is starting. And in here, actually, I'm just changing the initial values for the substrates, and then just reading the parameters energy to save the custom data. So so this was the seeding part. So we seed the cell, and we started the intracellular part, and during the main loop, we will update the cell and update the whole part. So in update intracellular, I will explain this one later, but we are just actually simulating in a parallel way, and I will explain this part later. And those are the same, like my coloring function and create cell circle position is a function to have a position vector to be assigned for the cells. Yeah, so the only thing is just the seeding part, and also we need to write the update intracellular, and this is called in the main loop. And let's look for the configuration file. We have seen that one a lot, but again, we can just look how it looks like. It's Roadrunner, and this one is not implemented yet, but we will discuss this one. We are just giving, I can just remove it because it will not affect anything. The SBML name, this is specific for the type. So what I can say, so I believe right now we are only supporting one SBML per cell definition for cell type. So if you would like to have more than one chemical reaction or any ODEs, you can just have this SBML that has two different set of reactions, and just make sure that they are not affecting each other in any way. And therefore, we are just giving one SBML per cell. And those are substrates, phenotypes, and the custom data. So the custom data is important because this is where we store the data. So after the each simulation, the cellular data will be storing the internal metabolite as a concentration. And so therefore, if we are simulating the in each DT and we are saving, let's say in each DT, then you should be able to see each concentration in each DT. Um, so therefore, the custom data are important. And as a user parameters, maybe again, like these are kind of like a user parameters, but they can be kind of like implemented in here, but they are not yet. So these are just parameters that we are just getting from the configuration file, and while we are seeding, we are updating the initial values. Okay, that was the part that I would like to show. We did a code walk, and okay, we have mentioned about the integration of kinetic part and PhysidFBA, kind of similar because the Boolean networks are more kind of like a gene regulation networks or so, but DFBA and the kinetic models are dealing with metabolic. Also, like the other ODs can be there, but the the DFBA has a similar approach. So flex wellness analysis. So the flex wellness analysis is kind of like um, because the kinetic parameters for the each reaction rates, finding those could be very hard. So therefore, scientists are trying to find a different way to have the metabolic model. So therefore, flex wellness analysis are just looking for the stoichiometric relationship, and then they are looking for the flux as a vector, and they are saying that the cell is in pseudo steady state. This is a very big assumption, I know, but this is how they started. So they say that like the okay, there is no accumulation of glucose or something. So therefore, we are just assuming they are not changing. So after we have D0, so therefore we can have a possible reactions based on the stoichiometric information. So based on this solution space, they are saying that there could be some constraint, by the way, sorry, there could be those all solutions can be there, and then they are putting some constraints like maybe thermodynamically, or maybe I don't know, like biologically or so, and they are just making small and small sample part, and then they are looking for one objective function, which is mostly biomass reaction rate, is like maximizing biomass reaction rate, and then they are choosing. So the FBA is kind of like looking for a very similar approach. So FBA is like taking a photo, and DFBA is like a stop motion video, which is kind of like taking a video. So the one thing important in here, so we don't have any intracellular part in the FBA. They are just looking for the available substrate in that voxel, and then if it is available, then the transfer reaction flux cannot. They are not constraining that flux, that reaction. If there is, let's say, glucose is depleted from the microenvironment, then they are saying that the glucose transfer reaction flux cannot be, let's say, higher than some values. And then they are putting like those constraints and then making an optimization to find the best uh, reaction reaction fluxes set. And then finding a biomass growth rate. So the thing is, the that growth rate is used as used in the volume calculation for growth of cell. So when you go for the PhysidFBA GitHub, what you will see is there are some volume calculations based on the optimization result. So if the cell is greater than that given threshold, then it's allowed to divide. As you can see, as you can remember, it's the arrest function. So this is how PhysidFBA is implemented. So I don't want to. Okay, so the time is. So the LibRoadrunner interactive demo, we will start actually like creating the domain first, but I just want to explain the model and some model rules, and then maybe we can have a break a little bit and then turn back and create the domain. I don't want to cut it in half. So so in our model, there will be 3 substrates: oxygen, glucose, and lactate, and energy is created with the 2 reactions. The reactions, one is aerobic and anaerobic, the other one which is creating lactate, and also the energy is consumed by one mass kinetic action. And there are some phenotypic tokens, which are migration speed, apoptosis rate, lactation secretion rate, and transition rate. The initial energy is for the 450. So I just want to remind that this is a kind of like qualitatively we are making a kind of like qualitatively modeling in here. So those are those values are not actually scientifically true. So we are just showing the behavior and also being sure that math is right. So if energy is higher than 445, then they are allowed to cycle. If the energy is less than 445, they are not. They cannot divide. And if the energy is less than 440, they are trying to escape from the hypoxic part. They are moving. And if they are reaching 430, they die. Those are the rules. And if you didn't, so maybe while we are taking a break, also please populate the OD energy sample like I did. I can do it again because I want to be sure that you have the LibRoadrunner in your machine. Yeah, let me stop my sharing. If you have any questions, by the way, we have 4 minutes, and I'm very happy to answer them. Okay, then I'm just stopping the recording, and then I believe the other one will start in 1:30. So let's meet in here again 1:30. Thank you.